Okay, folks, I'm just going to remind you of what we've done this year and where we are now, and then I can tell you what this actual video is about. We've covered all of these topics here, right down to there, to our topic 6, energetics, part 1, enthalpy, and we are aiming to cover 7, 8 and 9 before the end of the school year online. Currently, let me just explain what we've finished. We just finished Born Harbour cycles, as you know. That was done with TCs and so on that you did at home. And I sent you some videos as well. And now we're going to move on to chemical kinetics. And you can see how many units there are for chemical kinetics. And this video is going to be the third video to cover the first PowerPoint in this Unit 1 basic concepts. Here's Unit 1 basic concepts, and these are the success criteria you should address. But it's that PowerPoint there I've broken it up into 3 parts, and I'm going to make a third video of that right now, okay? So if I can just put this out of the way for the moment. And this is the third video, on that introduction PowerPoint, and it concerns methods of measuring reaction rate. Some of these you already know, okay? The first thing to tell you is that there are chemical methods and there are physical methods. And what I mean by chemical methods is you literally monitor the concentration of a reactant or a product as the reaction is happening. And it's a very messy method, okay? With physical methods, you don't do that. You can sit back and fold your arms and just record data that you see appearing on a thermometer or a data logger or whatever, okay? But both methods involve monitoring a change over time, okay? So this is the first one, the chemical method, monitoring the change in concentration of reactant or product with time, okay? So here we have a reaction occurring in a beaker. These are all the same beaker. This is at time 0 when you first mix them. Then this could be 1 minute, 2 minute, 3 minute. And the idea is that you take a portion, and the word aliquot is often used in exams. You take a portion, a sample, an aliquot at specific times, and then you quench the reaction, you kill the reaction. So for example, if there's an acid involved, you'd add an alkali to neutralize it and stop the reaction. And then you can analyze the sample for the reactant or product, and then you can plot a rate curve like this. It's messy because you have to disturb the system. You have to put a pipette in here, you have to add chemicals to quench, and you have to put a pipette in to take a sample, and so you're actually disturbing the system as it goes along, so it's not really ideal. The physical methods are much better, okay? Now there's one reaction that you've already studied. It's called a clock reaction, and in a clock reaction you just measure one time. You measure the time taken for a certain change to happen, and you just record that one time, okay? Now in a clock experiment you are recording the time taken for a certain point to be reached. It might be a sudden color change. Here we are. This is called the iodine clock, which I'm going to show you at some point, and something colorless will suddenly become black. If you blink, you miss it. It's really quick. Now, obviously, if the reaction rate was halved, then the time taken would be double, wouldn't it, right? Again, if the reaction rate was halved, it would take twice as long to make that change. So I've written at the bottom there, if the time taken for the change was doubled, then you can say the reaction rate is halved. That's how clock reactions work, okay? So I hope you worked out that the average rate up to the point where it changes is proportional to 1 over the time, okay? So if the time has doubled, then the rate is halved. If the time is quadrupled, then the rate is only a quarter of what it was at the beginning in your first experiment, okay? Couple of clock reactions that you will see with me as we go through the term. In the iodine clock, you have peroxide, which is being oxidized to oxygen. You've got iodate being reduced to iodine. And the iodine is then quickly mopped up by thiosulfate, which is also in the mixture, and it goes back to iodide. But eventually, the thiosulfate will run out, the iodine's got nothing to react with, and it reacts with the starch that's also in there, and suddenly becomes that blue-black color that you see in biology, okay? So that's the basis of how the iodine clock works. And there's another reaction, which is quite similar, not identical, but similar, and it's this time the peroxide reduced to water, and iodide is oxidized to iodine, but the principle is the same, okay? Now, it so happens in this reaction that if you have a total volume here of 100, a total volume, say 100 cm cubed, you could start with, let's say, 10 cm of peroxide and 90 of water. Okay, then you could have 20 of peroxide and 80 of water, or you could have 80 of peroxide and 20 of water. And what you can see is when the volume of peroxide is being doubled, in other words, when the concentration is being doubled, you can see that the time is being halved. Yeah, if you double the concentration of peroxide, you can see the time taken is being halved. If you double the concentration again, the time is being halved from that to that. So you can say in this case, the rate of reaction is directly proportional to the concentration of peroxide. Yeah, this particular graph is showing that the rate is proportional to the concentration of peroxide. And if you plotted 1 over time, which is proportional to rate, against the concentration, you get a straight line, proving that the rate of reaction is proportional to the peroxide concentration. This is the cross on the paper experiment that you did when you were in year 9 and again in year 11. It's thiosulfate reacting with acid and the solution becomes cloudy, and you might remember looking down and seeing a cross, and you took the time taken for the cross to disappear. Okay, so that's a similar type of experiment. Here we go. Acid added to thiosulfate, put it on paper, then it becomes like this and it gets cloudier and eventually you can't see the cross. Okay, and once again we find that the time taken is inversely proportional to the concentration of thio. If the concentration of thio is doubled, then the time is being halved. So we can say that the rate's proportional to the thiosulfate concentration. Now, there's another method you've used before when you were younger students. You can look at the change in mass of a system as gas is produced. So if you have a gas produced, you can monitor this mass here against time, and you get something like this. And I hope you can see which is the fastest of those two reactions. Yeah, it's the blue one because it's steeper. The mass is falling more quickly. Obviously, they will level off like this, but they won't reach zero, of course, because the glass weighs something, doesn't it? It will never reach zero, but it will level off. Okay. There's another way you can treat this, and that is every so often, let's say half a minute, you can record the mass, you can subtract it from the initial mass, and you can get the mass of gas produced up to that time. And you can keep doing that. Another half minute along here, take the mass, again subtract it from the beginning, and get the mass produced up to that point. So here you can see in half a minute I've produced 0.58 grams, and there we are, there's my first point on the graph, 0.58 against half a minute. And you can keep doing that, keep subtracting from the initial mass, and you'll get a rate curve, total mass of gas against time. Okay. Another one is measuring volume of gas produced. Now this is a gas syringe that hopefully you've seen before. It's very tight fitting, no gas can escape. The plunger fits in tightly like that. And here we are, gas being produced, and you can measure the volume of gas against time. And again, you'll produce a rate curve of some kind. Here we are, oxygen gas in this case, all right? Now this one you haven't seen before, looking at the absorbance of light by a reactant or product using a spectrophotometer or a colorimeter, not a calorimeter, a colorimeter. Okay? Now look at this blue substance here. The reason why it's blue is because when white light is shone at this, it's absorbing all of these wavelengths here, particularly this one, look, big absorber, but it's not absorbing here, and it's not absorbing far to the right here. So a mixture of these colours and these colours, which are being transmitted, gives us that colour that we see. All of these are being absorbed. Okay, and this colour wheel is in your data book. If a substance is absorbing here, then you will see this colour. If it's absorbing there, you will see that colour. So in the one that we just saw, it's absorbing all of these green and yellow wavelengths. So we look at this here. It's absorbing these wavelengths. So over here, you see this kind of mixture here. You see these colors here. Okay. Now, chlorophyll, you know, doesn't absorb green. That's why you see green. It's absorbing these wavelengths here. But the reason you see green is because it's not absorbing green. Okay. Now, if you had chlorophyll in a spectrophotometer or a colorimeter, if you selected a green wavelength, of course, it will go straight through. It'll be transmitted and the absorbance will be low. Okay. The green wavelengths here are not absorbed. If you select blue, then blue is absorbed. That's why it's green. So the absorbance, look on the meter here, the absorbance is very high. It absorbs the blue wavelength. Okay, so that's the basis of using a colorimeter or a spectrophotometer. Okay, so there we are, white light source, skinny beam, select your wavelength. Here's your sample, and you can measure the absorbance like that. And the absorbance is proportional to the concentration for a given wavelength and a given path length, because if the tube is wider, then of course there'll be more absorbed. Okay, the sample's normally put in cuvettes like this, and here's the spectrophotometer. But now we use, this is about the size of a smartphone, we use a colorimeter and a data logger using Logger Pro, same cuvettes, but we can see the absorbance on a data logger there using your laptop. And absorbance is proportional to concentration for a given path length and a given wavelength, and therefore we're going to get a straight line graph going through zero. Okay, and this is a calibration curve. So if you had a solution of unknown concentration, you could pop it into the colorimeter, you could measure the absorbance, and you could read off the concentration. That's what it's for. Okay, before you use the colorimeter, you have to use a blank. So you have the cuvette with only water in it. You put it in, you press 0, so the colorimeter is ignoring the glass, ignoring the water. Then you put your sample in, and then you get absorbance for that particular concentration. And we use the Beer-Lambert law there. Okay, so here this reaction here is producing iodine, and it's getting darker and darker brown. You can see the absorbance is increasing. And we can then draw a rate curve if we want to. Okay, so we can see the absorbance is increasing, and the absorbance is proportional to concentration. So this is effectively a rate curve. Sometimes the absorbance goes down because you begin with a colored substance and it becomes colorless. Okay, and there's some other methods of monitoring rate I want to measure briefly. If H plus or OH minus is consumed or produced, then the pH will change. So you can monitor the pH against time, and that gives you a measure of rate. Okay. Another one is sometimes there are ions produced or consumed in reactions. So in this reaction here, there are ions on the left, there are no ions on the right. So the conductivity would decrease with time, and you could use that as your measure of rate. And finally, if a gas is consumed or a gas is produced, you can monitor the pressure of a system at constant volume, and you can see the pressure on a pressure gauge, and that will give you some measure of the reaction rate in terms of the gas pressure. Okay, so we've finished.